First got introduced to physics. What is mechanics to you? What is mechanics? Huh? Mechanism of what? Well, why not physics in general? So, mechanics is a part of physics. That's how we understand it, right? It's a major part of physics. But what you're saying is almost like the definition of physics. It deals with mechanisms of matter and energy, nature, and so on. But what is mechanics in particular, to be more specific? What do you do in mechanics? Anyone? So typically, it has to do something with the motion of objects. Could be addressed as well. Typically, in general, it has to do something with the motion of a particle or an object with respect to time. So the essence of mechanics in general is to find the position or the displacement of a particular particle or an object as a function of time. Be it the position of an electron inside the atom, be it the position of the moon, which is revolving around the earth, or the position of the earth moving around the sun. So every such motion is quantified by means of this subject called mechanics. And there are certain rules to it. And the basic ones that you know come from basically Newton's laws. So Newton's law, so what is the essence of the first law? Once we discuss mechanics, automatically Newton's laws come in. So the first law is something which tells you about the nature of a particular physical parameter, which when acted upon on an object which is at rest, brings it to motion, and if it's in motion, brings it to rest. It's something called the law of inertia. And what is that external something that you must do to the object? Louder? Force. Exactly. So force is this external agency or this external kind of stimulus that you need to provide to an object which is at rest to bring it to motion, and vice versa. An object which is in motion, you can bring it to rest via the application of an external force. So force is that parameter which basically provides that impulse, not the impulse, the stimulus to bring something to motion. Once the motion is happening, then what is the kind of crucial thing that we want to understand? Suppose you know how to kind of fire a rocket. Now that the rocket is in orbit, what next do you want to know? The direction, exactly.
How far does it go?
How far, to be more specific, how is it positioned at a particular time? So, there comes in the displacement as a function of time. You fired the rocket, very good. As time evolves, the rocket is having its own trajectory. Right? So, at a particular time, if you are interested in finding out the position of the rocket, therein comes in mechanics. And once you find out the position of that object, the rest is just a follow-up exercise. Knowing x of t, that is the displacement as a function of time, what next can you find? What is the rate of change of displacement? The velocity, right? So once you know x of t, you know v of t. Once you know v of t, you know the acceleration, which is dv dt. So you see, the essence of everything here is to find out the position as a function of time. And this is where Newton's first law, which basically is nothing but a qualitative definition of force. And the second law tells you what? What is Newton's second? That's true, but the actual law, I mean, people seldom kind of take F equal to ma to be the actual law. You're right, F equals ma is true, provided only if the masses are constant. If the mass is not constant, like we were talking about this rocket example, you might know, or kind of obvious, that when the rocket is fired, launched, and this is not your Diwali rocket. The Diwali rocket also kind of has the same principle, but these are really, let's say, the NASA rockets. Okay. Have you ever seen these videos of rocket launches? Yes. Or satellite launches? Yes. You see a huge amount of fuel being burned, and the entire space is kind of smoky and all. Right? What does that do actually? Why do you need so much of fuel to burn?
Make it.
Exactly. The more you exert with the fuel being burned, the more is the force or the reaction force on the rocket, which kind of pushes it up towards its trajectory. Now, when the fuel is burning, the mass of the rocket is no longer the same. Right? Initially it was, let's say, m1. Then after a certain percentage of fuel is burned, it reduces to another m1 prime. Right? So, going back to the statement of the second law of Newton, if you have velocity, which is, as you know, is dx dt, right? So the momentum, or the linear momentum, is m times v, mass times velocity. So the second law is basically the fact that the rate of change of this momentum is actually the force. Now, if P equals mv as it is, you see only if m is constant, you can put it outside the differential. If m is a function of time, like it so happens in this rocket example, rocket propulsion, the mass is a varying mass because the fuel is burning with respect to time. So the rocket mass is varying. So m in that case is not constant. You cannot really pull it out outside the differential and say that f equals ma, right? So rate of change of momentum equals force is a state. Now obviously, as in most cases we will discuss, m is a constant. So you can pull it out of the integral, the differential, and then which is this. Then you are perfectly out. So the first law was the definition of a force. The second law is a quantification of the force. And the third law?
Reaction.
Exactly. The effect of the force. So that's how the framework of Newton's three laws is. The first one, the qualitative definition of a force. The second one, quantification. How much? I know what a force does, but I do not know. If you do not let me know the second law, I do not know the quantification. How much acceleration, how much velocity causes what much force? That this law will tell you, the second law. And the third law will tell you that no force in nature can appear alone. There has to be a reaction pair. Forces always operate pairs. So these are the action-reaction pairs, and this famous statement of the second law, every law has every force has an equal and opposite reaction. Every action. But keep in mind, as is often the misconception, that action and reaction pairs work on the same body. No, never. If that had been the case, then nothing in this universe would have moved. The action and the reaction are working on the same body, the same magnitude, and exactly the opposite direction. So every other force in nature would have cancelled each other. We wouldn't have sensed anything called motion. So, for example, this laptop is resting on the table. So it's exerting a force equal to the mass of the object, which is the laptop, times gravity onto the table. And the table is providing a reaction force on the laptop. So the reaction force is appearing on the free body diagram of the laptop. So have these things clear. We'll talk about it again when we actually discuss Newton's law. So the point of going back to forces, that's the external agent which actually causes the motion. And once the motion has taken off, then you are interested in finding out the displacement or the position as a function of time when it comes in mechanics. Okay. So, talking about forces, what kind of forces or what nature of forces do you know?
Pseudo force. Pseudo force.
Pseudo force. Well, what I actually wanted to ask is, what are the real natures of force, or what kinds of force do you know? Pseudo force is like a centripetal force sometimes. Depending upon the frame of reference, you may or may not have that force. In that sense, it's a zero. It depends on the frame of reference. But what I'm asking you is, an object falling onto the ground, what force is that?
Gravitational force.
Electrostatic. Good. Okay, let me just illustrate. Okay. So, gravity or gravitational force. You said electrostatic. Good.
Electromagnetic.
Magnetic. Magnetic. Okay.
Frictional.
What else?
Frictional.
Friction. Did you say friction or what? Friction. Friction. Okay. Friction. Centrifugal. I'll write it down. Still.
Centrifugal.
Anything else? Inertia. What?
Buoyancy.
Buoyancy. Buoyant force. Okay. Buoyant force. But before proceeding further, do you think all these forces are kind of, except gravitational maybe, which is the fundamental force? Because it only depends upon the masses of the two objects and the interaction of the distance between them. Now, centripetal iron or buoyancy, the force of buoyancy, centripetal, as I said when he was mentioning centripetal, it's a frame force in the sense, suppose you are revolving around something as the earth is doing, or when you, have you ever taken this merry-go-round, the horizontal ones, or even the vertical ones? It's scary for me. Yeah. I tried once, the vertical one, I screamed so much they had to shut down the machine and take it out. It's still okay. So, while doing this, I can take the horizontal one, not the vertical. Anyways, so the horizontal one, if you have taken a merry-go-round, or even if you have, when you have a curved road, rent your car, or the vehicle you are moving in, you sense this force which kind of takes you outward, right at the curve edge. So that's basically the centripetal force. That only happens because you are moving in a curved path. So that's a, and this force won't be sensed by an observer who is at rest outside the bus or the vehicle. So in that sense, it's an inertial force. Force of buoyancy or the buoyant force is also a reaction force provided by the container or the vessel which is immersed inside the liquid. But I am talking of fundamental forces like gravitation. What other forces of a fundamental nature do you know of? Electrostatic and magnetic are close, but as you might already know, electricity and magnetism are basically the same phenomenon. What we call as electromagnetic forces. So, gravitational is a fundamental force. Electrostatic and magnetic combined, we call it
Electromagnetic.
Friction. Friction is interesting. Friction is still a huge body of research actually in physics. The origins of friction. So friction has actually its origin in electromagnetic interactions. Friction is what? When you have two surfaces in contact, try to move one with respect to the other, you feel or you sense how the object feels a force of friction. Right? So at the microscopic level, at the atomic level, it's basically the electromagnetic interactions between the atoms of the two surfaces, which is actually the origin of friction. So friction is not a fundamental force. So this, basically this. Again, as I said, centripetal and buoyant, they are, one is an inertial force depending upon whether you're taking a curved path or not. So these are not fundamental forces. So gravity is fundamental, EM is fundamental. There are two other forces in nature which are also fundamental. Nuclear forces, good. To be more specific, there are two categories of nuclear forces. Strong and weak. Exactly. So there comes the, I'll skip a couple of slides and go to the fundamental forces. You see, electricity and magnetism combined into electromagnetism is one fundamental force. And light, as you know, is an electromagnetic field. That's why it's in this manner. Gravity is another fundamental force. Nuclear forces. So magnetism and gravity are such forces which occur at scales which might be as tiny as an electron and an interaction between a nucleus, because both have masses. Whenever you have masses, you have gravity. Be it as small as electron and nucleus, or be it the Earth and the Moon, or the Earth and the Sun. All it involves is masses. It might be very tiny, but it's still there. Okay. Electromagnetism is also a long-range force. But these nuclear forces, like the strong and the weak, they are operative at nuclear scales or atomic scales. So the weak force is one force which comes into picture when you have radioactive decays. You might know of these alpha and beta decays of the nucleus. So the forces operating there are called weak interactions. Interaction, whenever I say the word interaction, it means forces. So that's there. And then for the strong interaction, well, what is strong about it?
Same charge current.
Can't be broken. What can't be broken?
Electrons.
You have a sense to it, but yeah, I'll tell you about it. So have you ever wondered as to the fact that we all know that the protons inside the nucleus are positively charged, right? Now, for most of the elements that we know of, okay, the nucleus in itself has so many of these protons packed together inside the nucleus. And what is the kind of size of a typical nuclei? Of the order of a femtometer, 10 to the power minus 15 meters. So have you ever wondered as to why so many positively charged particles are able to reside within that tiny nucleus without really exploding the nuclei and kind of breaking apart the atom? Had it been purely electrostatic, then it should have broken the nucleus. Huh? Can you really pack those many number of, imagine the elements having higher atomic number, right? For the hydrogen atom, it doesn't really matter. It only has one proton and one neutron, and an electron. That's the simplest atom that we know of. But now, for higher and higher elements, you have so many protons. The neutrons are neutral. Forget about them inside the nucleus. But so many protons packed together. So what happens inside the nucleus is, via these interactions called strong interactions, these are exchange forces. Okay? So there is a physical process, a reaction through which it occurs. that force there is something called a strong interaction. Okay. So basically these are the four fundamental forces, and the belief, the strong belief, or kind of an ultimate goal of theoretical physics in general is to unify and see all the forces in a single frame. So the belief is such that you all know about the Big Bang or heard about it?
Yes.
Big Bang.
Big Bang theory.
What is it?
Evolution of
Evolution of the universe. Okay, partially true. It's basically the origin. So the concept is all of this matter in the universe, or the universe itself, started from a huge explosion at a certain point of time. So that explosion itself is called the Big Bang. So right from the beginning of the origin of matter, time also is supposed to start. Because if you do not have space, as such you do not have the concept of time. It requires some people thinking, but actually that's what Einstein did. He did all these theories where space and time have been brought to the same level. If you do not have any concept of space, there is no time in it. So Big Bang was that event which gave rise, or that was the origin of the universe, and hence matter. Now, the belief is that right at the point of this Big Bang, all these four forces were actually unified. You couldn't really distinguish one from the other. But as time evolved, of the order of 10 to the power minus 9 or minus 10 seconds, at that scale, the forces started segregating from each other. Okay. Now, what physicists have been able to do is combine electromagnetism with weak interaction. They have already formulated, and this is a well-known and established theory for which the 1971 Nobel Prize in Physics has already been given. So electroweak theory, it combines electromagnetism and weak interaction, and has shown that these two forces are basically of the same order. Likewise, the strong interaction along with the electroweak interaction has been integrated via something called the standard model, which people are still researching on from 1976. So that's part of the standard model. Now, gravity is the disobedient child. Gravity is very difficult to kind of integrate into this entire picture. So once gravity is integrated via, well, this was already during Newton, universal gravitation. Then came in Einstein with his new concept of general relativity, which actually combines, I shouldn't say combine, but showed in sharp contrast to what Newton had, that gravity is basically an output or consequence of space-time being curved. Now all these are terms which I know might be kind of hand-waving rather than, if you do not really discuss the physics, then this doesn't really make much sense. But if you guys are into watching Big Bang Theory, anyone? There's a television series, Big Bang Theory. Is anyone into it? No? You are? Do you watch Big Bang Theory, or have you watched? Okay. So would have been interesting if more people were into watching this. It's a comedy American television series, okay? And it's about a group of four physics graduate students, PhD students. I think they are from Stanford or California, Caltech. And they kind of do funny things, I mean, and that integrates many physics concepts. So it's a very wonderful watch, at least to me. So there is this, it's only one of you. Who is your favorite character in Big Bang? Huh? You actually? Let me come close. Oh, 3 to 4 episodes. Okay. So there is this guy called Sheldon. If you, in those 3 or 4 episodes, he must have appeared. So Sheldon is the most nerdy, nerdy kind of a guy who kind of knows everything about everything. So Sheldon often keeps on talking about something called string theory. Have you guys heard about this term called string theory? Okay, so never mind. So string theory is the latest theory which actually tries to combine the standard model with general relativity such that the ultimate aim of physics, which is to combine all these 4 forces into this grand unified theory, popularly called GUT or sometimes unified field theory called UFT. So that's like the ultimate goal of physics, where you want to combine all the 4 forces as one, which was actually there during the time of Big Bang. Okay. So that's regarding what the fundamental forces are and how over the years people have gone through many stages of research and combined all of these together. Okay, so what scales? So physics, as we know, runs from atomic scales or subatomic scales right up to astronomical scales. So I'll go back a couple of slides just to give you an idea, and you should really have this idea now that you are already in college or university, as to when you talk of something, how much is the quantitativeness to it? If you talk of an atom, what is the length of an atom or the diameter of an atom? Right. If you talk of the cells in your body, what is the magnitude of that? So all these quantitative aspects, starting from a typical length of a human being, which is of the order of a meter, 1 meter, 1.5 meters, right? So this is below the scale. See, a blood cell, a red blood cell in our body is typically 10 to the power minus 6 meters, which is 1 micron. 1 micrometer is 10 to the power minus 6. Go to an atom, typically 1 nanometer or an angstrom in diameter. The atomic nucleus is typically 1 femtometer. Likewise, there are atometers, femtometers, forget about it. But right down to the Planck scale is 10 to the power minus 34. So that's something called the Planck scale. And you already know about this H called the Planck's constant. You remember the figure for the Planck's constant?
10 power minus 34.
Minus 34, exactly. So therein comes the Planck length scale of 10 to the power minus 34. That's the shortest of the scales all these theories that I have been talking about, those are the shortest scales which those theories handle. Especially the strong and the weak, because those are the ones which are operative at that scale. Okay. So this was below 1 meter, and then the next slide you see. Next one, starting again from atomic scales, subatomic scales of quarks, it goes up to the observable scale of the universe, which is about
28
meters. This is meters. Okay. So the existing universe is starting from this atomic scale of Planck's length to a cosmological scale of 10 to the power almost 30 meters. So that's the range over which you need to unify the forces. Forces at the subatomic level, weak and strong, 2 forces occurring at large scale forces like gravity and electromagnetism. So they would be operative at, not operative because again as I said, even tiniest of the objects will have gravity between them. But they are more superseding, more overwhelming on those scales. So the range that I talked about in this slide here is basically combining subatomic to the cosmological. This is just to give you an idea as to how the length scales of various objects are, and what are the concerns and what are the forces occurring at those scales. Not that we'll be learning about weak forces and strong forces in this course. This is more of that would be more of a pure physics kind of a course. This is an engineering physics course. And at the same time that you are taking your physics course, you should really know that there are 4 fundamental forces in nature, and this is the status of things in a single cell. Okay. Okay. And just to kind of elaborate on that a bit, you see the 4 fundamental forces on the left. Gravity acts between objects with mass, and the particles which are experiencing gravity has to be particles with mass. So neutrinos, which are kind of massless particles, would not experience gravity. You need to have mass, and corresponding to each of the forces, there are particles or force carriers associated with it. For gravity, it's something called graviton, which hasn't been experimentally discovered, but it's theoretically proposed. And the range of gravity is infinite. Why is it infinity? Because that R that appears in the law of gravity, gravitation, that could have any range from 0 to infinity. 0 in the sense, from small scales to infinity. So gravity is the weakest of all these forces. Then comes B, which governs these particle decays, radioactive decay and all. And the particles which are experiencing those are called quarks and leptons. And the force carriers are these particles called W and Z. This is just qualitative information. So you need to appreciate that whenever forces occur, they occur through force carriers. And these force carriers are in fact these elementary particles. Graviton, the W and Z particles. For electromagnetism, in fact you know this, the photon. The photon is like the quantum, h nu. It is like the quantum of electromagnetic interaction. And again, just like gravity, it is a long range force, so it's infinity. And finally, the strong force, which basically binds quarks together. What are quarks? Does anyone know? Quarks? Okay. So, electron, as you know, is a fundamental particle. Why is it fundamental? Why do you call it a fundamental or an elementary particle? Because the electron cannot be broken down further. Electron is just an electron. Nothing beyond that. But if you break down a proton, you find these quarks. So proton is not an elementary particle in the same respect as an electron is. So protons can be broken down into something called quarks. Again, quarks have varieties of their own. The top quarks, down quarks, up quarks, down quarks. They have something called colors and flavors of their own. I mean, not physically, you cannot really taste a quark, or cannot really see it under a microscope and say that this is a blue quark, this is a green quark. No. But these are names, nomenclatures, which appear from something called quantum mechanics, which is beyond the scope of this current syllabus. But the mechanics which is operated at those atomic scales is no longer classical mechanics. It's no longer Newtonian classical mechanics. The laws that govern nature at those scales are governed by something called quantum mechanics. So you might have had a glimpse of it in your high school. For example, do you know of this uncertainty principle?
Yes, sir.
Heisenberg, right? What does it say?
It is not possible to find.
Right, momentum and position. Exactly. Good. Very good. So, you see, already, if you go by Newton's law, the equations of motion, everything is kind of absolute. Why is it absolute? If you tell me the position of something, at a certain time, I can just do dx dt and find out the corresponding velocity. It's exact, but this is all from Newton's law. But now Mr. Heisenberg already says that you cannot measure the position and the momentum. Momentum involves velocity. That is to say, you cannot measure the position and the velocity with simultaneous precision because of this h bar factor that comes in the Heisenberg principle. So you already have a sense. Again, this is all valid where or most visible where in the atomic scale. If you are doing mechanics of the Earth or the stars, this may not be apparent because these are huge objects where the position and the momentum are exactly calculated. Okay, so it all becomes apparent when you go to these atomic scales. Again, why is it apparent there? Because of something called the wave-particle duality. It shows up at those scales. There's something called the de Broglie wavelength, right? So the de Broglie wavelength associated with a certain object is very much prominent at those scales. We also have a de Broglie wavelength associated with us. We should also obey quantum mechanics, and we do. But the thing is that the quantum mechanics for us, like objects like us, are such massive that it doesn't show a difference. If you do this delta x times delta p, it will all be like Newtonian mechanics. It doesn't make much. Okay. So the thing to appreciate is quantum mechanics is the mechanics which is the mechanics for these atomic scale particles. So all these quarks and gluons, they all obey, in fact electrons as well, they all obey quantum mechanics. So all these terms that you see here and terms like top, up, down, color, flavor that I talked about are terms which are called quantum numbers in quantum mechanics. Okay, anyways. And the fourth scale here is G, which is the gluon for strong forces. And it so happens that each of these particles, these exchange particles here, are actually particles. So particles in nature typically have two broad categories. One is called bosons, arising from the name of Satyendranath Bose. The other is called fermions. So electrons, protons, these objects are all fermions. Why they are fermions and so on, again, that would be a long discussion. But just appreciate the fact that broad category of particles, elementary particles, you have bosons and you have fermions. All these exchange particles in nature, they are actually bosons. And here is a quick structure of the atom which actually shows the UUD. So these are all quarks. This is just to show that although the electron is fundamental, you see there is no quark sitting inside the electron. Electron is just electron. But if you break down the proton, inside it you will find these quarks. Okay. And as I said, the exchange particles, that is the photon for electromagnetic radiation or interaction, the gluons for strong forces, the W and Z particles for weak forces, and the graviton for gravitational force. These are all bosonic particles. And here you find the nature of these particles. Photons are massless, no charge. Gluons are high mass, color range, strong force carriers. W and Z particles are high mass, weak force carriers. Graviton is massless, no charge, gravity force. Okay, and this is a fun slide which talks about the four forces. Okay, and again, this slide is basically showing you the strength, the relative strength of the four forces. You see, gravity is the weakest. Observe, if this is on a scale of 1, if you say I will give strong force a count of 1 in whatever unit, then gravity in that same scale would be as low as getting on minus 39. So it's that weak as compared to a strong force. So gravity, then weak. You can also see the strength, the relative strength here, and the range of the forces. Oh, so gravity is strong. And as I was saying, quarks contain, they have colors associated with it. This is again a slide which basically shows you that quarks can appear in various colors, green, blue, and red. And as you know, a combination of all these colors gives you white. So this is white. So for this session, and maybe I'll go on to discuss Newton's law from next time onwards, or rather, what I plan to do. So the idea for today was to make you appreciate the fundamental forces of nature. So what we learned today are that there are 4 fundamental forces of nature: gravity, electromagnetic, strong and weak. And the range of these forces, where are these forces more effective? Gravity and electromagnetic, long range forces, strong and weak, atomic range, or nuclear range. Right? We learned about the force carriers which are involved in the interaction of these forces: graviton, photon, gluon, and the W and Z particles. Okay? And so that was pretty much it for the, like, it was like a broad picture of how you should see forces. And all these forces that we talked about, like friction, you might also think of elastic forces. I thought someone would mention elastic forces. No one did. Because when you have the springs and all, you typically think of Hooke's law and think of elastic forces. Elastic forces, again, the origin is actually electromagnetic. That's why elastic forces are not fundamental forces. So that was the appreciation I wanted you to have. From next time onwards, that is from tomorrow, we'll be doing, so obviously in order to, since you see that mechanics basically concerns forces and displacement and velocity, acceleration, and so on. But all of these physical parameters are vectorial in origin. They are vectors. What does that mean? They have magnitude and direction associated with it. Very basic. So first, what I'd like to do from tomorrow is to go through a review of vectors and the coordinate systems. You're already aware of the Cartesian system, the XY, Z or Z system. We also have the cylindrical polar system and the spherical polar system. So if you haven't gone through those are the ones we'll go through. And obviously vectors as compared to scalars, the rules for vectors are a bit different because they have directions associated with them. Vectors do not just add up like scalars. 3 plus 5 for scalars, both the numbers, gives you 8. But since now vectors have directions, in order to add up vectors, you need to have certain rules. So basically we'll be doing vectors from tomorrow onwards and coordinate systems, and then move on to Newton's law. Okay, so that's it for today, but obviously before you leave, I will take your attention.